Okay, so this talk is actually going to be pretty closely related to the talk we had just seen. We're looking at how we generate PTX intermediate representation code, which is the intermediate representation used for NVIDIA GPU architectures. So one of the clients of this is to take OpenCL code and compile it for NVIDIA architectures. So first we're going to start and look at, well, what is the PTX ISA. Then we're going to look at how we do PTX code gen within LLVM. Then we're going to run through an example. So the first question to ask is, well, what is PTX? As an acronym, it stands for Parallel Thread Execution. It is the intermediate representation for NVIDIA GPU architectures. In the interest of time, I'm not going to necessarily go over how we write GPU applications. I'm going to assume some knowledge of, say, thread blocks and how you decompose your problem into these. So if we look at a piece of PTX code, what we're looking at is what a single thread of execution does. Now, on the GPU device, there will be potentially thousands of these threads actually executing, so we're looking at what one of these threads does. The PTX ISA itself is a RISC-style instruction set. So you can see that you have your standard load, stores, multiplies, adds, operating on some register file. One interesting thing about PTX is the actual register file is an abstract register file. So you have to actually declare what registers you're going to use, and there's actually no preset names. You can call them whatever you want. You just give them a type, and then you can specify how many of that particular name you want. So for instance, if we define 6 RD registers here, that will define for us RD 0, 1, 2, 3, 4, and 5. So why do we care about supporting this PTX code? This will allow us to use LLVM to generate code for NVIDIA GPU architectures. So this allows us to take advantage of all of the existing optimization and analysis work within LLVM, as well as any new optimizations that we can write specifically for GPU targets. We can also use this as a way of writing new GPU-aware languages. For instance, we can write language that compile to LLVM IR, and then we can simultaneously compile those for x86, for ARM, for PTX, for whatever ISA we actually want to target. We're also interested in looking at heterogeneous systems. So if we look at the current crop of GPU architectures, these things can have up to 2 teraflops of peak compute power. We want to be able to take advantage of these specifically for applications that have a lot of actual floating point code. So to target these types of systems, we can take a single application, generate x86, ARM, or whatever backend you want to use for the bulk of the program, and basically generate PTX for specific parts that can be easily offloaded to GPU devices. So this would allow LLVM to basically take advantage of these heterogeneous architectures. Okay, so how do we do code gen in LLVM for PTX? So a brief history of the current state of the actual backend. In September of last year was the first commit to this backend into the LLVM source tree. Since then, it's been very actively developed by myself, Shailing Chow, and Dan Bailey. It was also my Google Summer of Code 2011 2011 project where significant work was done. And technically, the first release of this backend was part of LLVM 2.9. Now, when the 2.9 branch happened, there was very little implemented, so it's basically not usable in LLVM 2.9. But as of the 3.0 release, it is very much usable now. So currently, what works in current LLVM trunk, which at this point also means LLVM 3.0, since we haven't changed anything major since the actual branch, most of the actual compute functionality works. So we can write GPU kernels in LLVM IR, compile them to PTX, and execute them on NVIDIA GPU devices. We also support branching. We can access special registers within PTX. So for those of you familiar with PTX, the way a thread figures out which thread it is, what its thread ID is, what its block ID is, that is accessed by actually reading special registers in the PTX ISA. So we define LLVM in intrinsics, which allow the IR to actually read these particular registers. We also support device function calls. At the moment, this is very basic support. However, you can write kernels in LLVM IR that make calls to device functions also written in LLVM IR. One of the major points of what we can support as of LLVM 3.0 is the interop with the Clang OpenCL support. So now you can compile OpenCL code with Clang, compile it to PTX, use the NVIDIA SDK to load it and actually execute it. And we'll see an example of this later. And finally, well, not actually finally, this is just a list of some stuff that's implemented. We support reading and writing from the shared memory regions on GPU architectures. So for those of you who are familiar with GPU architectures, you'll know that taking advantage of shared memory, or local as it's called in OpenCL, is very important to achieve high execution speeds. Okay, so if you have a up-to-date version of LLVM, how do you use the actual backend as it is now? So basically, all you need to do is build it as part of LLVM. So depending on which build system you're using, AutoTools or CMake, all you have to do is say, go ahead and build the PTX backend. It's part of the LLVM source tree, so you don't have to worry about downloading anything in addition to LLVM. And then you can use the PTX 32 or PTX 64 targets. These correspond to the two addressing modes within PTX. So within PTX, we have pointers. So depending on if you're compiling for, depending on if your host code is compiled for Intel 32-bit or Intel 64-bit, you'll have to use the corresponding PTX version, so the backend uses the right pointer size. Once you have PTX code, you can either use the CUDA Driver API or the NVIDIA OpenCL SDK to actually load and execute this. And again, we'll see an example of this later. So in terms of the specific processes you can currently target in the PTX backend, we've defined targets for the different compute models. We've defined targets for the different shader models, as well as a couple definitions for specific NVIDIA processors. We also support different options. You can actually override which compute model or shader model you're using. Now, of course, if you specifically target compute something or SM something for a specific CPU, then you probably don't want to be using these options. But we also have some, for instance, to allow double precision arithmetic. In older generations of NVIDIA cards, double precision arithmetic might not be supported by hardware, and so you might have to cause all doubles to be demoted to floats. However, if you have a newer card, you can go ahead and use doubles directly, so we have an option to get rid of the automatic demotion from double to float. You also have a way to disable some of the optimizations we do, such as we can fuse multiply add instructions, but depending on your kernel and what you actually want to achieve, that might not be what you want. So of course you can disable things like that. And you can also target specific PTX versions. So let's say we want to compile OpenCL code and run it on NVIDIA devices. So we have one or more OpenCL kernels here and a group of host files. So these files will define the host code that actually makes the OpenCL calls. On the host side, we can run Clang just like you would for any other application, except you link with the NVIDIA OpenCL runtime. For the OpenCL side, you can use Clang to compile into PTX. Now, in order to support OpenCL built-in functions, we use the libclc library, which is being developed by Peter Collingborn. I think I saw him here earlier. I'm not sure if he's still here. And that's available at this address here. So the other important point to note is if you're compiling OpenCL code, or really any code that you want to use with the NVIDIA OpenCL SDK, you always have to use the PTX 32 target, and you have to compile for PTX version 2.3. And anything else, and the NVIDIA SDK will not actually accept it. So in order to do that directly from Clang, we can just pass some simple options. We can say we want to target PTX 32. We're going to give the actual backend a couple flags here to say we want to target PTX 2.3 and shader model 2.0. So here we're assuming we're going to run on Fermi class hardware. We're also going to tell Clang where to pick up the header files that are part of this libclc library, and we're going to force include the CLC header file. This is what actually defines the OpenCL built-in functions. Finally, we have to specify -s on the actual command line. So PTX does not have an actual binary format that we can actually use. So if you compile without -s, of course, Clang will try to run PTX through the system assembler, and that, of course, will not work. So you have to specify -s to make sure that what you get back is text PTX. Now, if you want to step outside OpenCL and look at, say, a domain-specific language in implementation, the model is more or less the same, where you can bring in some source for whatever domain-specific language you want to actually build. You can compile it down into multiple LLVM IR representations. One for the actual bulk of the compute code, where you can run that through LLC and get PTX code, and then you can also create LLVM IR code for the host device, which is what will use, say, the CUDA Driver API to load the PTX, copy any needed data to the GPU device, and actually execute it. So what do you need to do in order to write LLVM IR that can make the best use of the PTX backend? First, there's different calling conventions to use. We have the PTX kernel and PTX device calling conventions. Of course, PTX kernel is used anytime you write a GPU kernel, say in an OpenCL kernel function or in CUDA a global function. You will use PTX device anytime you want to write a function that will be called by a kernel function. And depending on what actual shader model you're targeting, that will determine how the calling convention is actually implemented in terms of which registers are used, or whether or not you use registers versus different types of ways to pass these things. You cannot make calls to kernel functions within LLVM IR. kernel functions can only be invoked by the host code. So anytime you want to make a function call in a kernel function, it has to be to a device function. Also, if you're targeting less than shader model 2.0, you cannot have recursion. Like I mentioned earlier, we also have LLVM intrinsic functions to access the different special registers within PTX. So for those of you familiar with CUDA, you'll be familiar with thread index, block dim, block index, grid dim, and so on. These, of course, map to special PTX registers, which we can expose using these intrinsic functions. We also have access to the sync instructions, which is the equivalent of sync threads if you're looking at CUDA code. Okay, so looking at the design of the backend, this is based on the LLVM selection DAG in infrastructure. So it's based on the same infrastructure as the ARM backend, the x86 backend, and so on. We used TableGen to define all the instructions and the actual pattern matching between LLVM IR, or sorry, the selection DAG IR and the PTX instructions. Recently, we've converted to use the MC infrastructure to actually do the assembly printing. However, as PTX does not support binary object files, we of course don't have a way of directly emitting object files. We use address spaces to differentiate the different types of memory within PTX. For instance, we use address space 0 as our global address space and address space 4 as our shared address space. So these correspond to the global and local address spaces within OpenCL, and Clang knows that this mapping exists specifically for the PTX backend. Of course, in the future, we want to try to implement the PTX unified addressing, so you don't have to use address spaces, but that's something to do later. In terms of things that we haven't implemented yet, we don't have texture or sampler support, meaning you can't actually bind textures and read from them. We also don't have vector support. PTX itself has limited support for vectors, which we hope to implement. Now, if your LLVM IR code just uses vectors in very simple ways, LLVM itself is smart enough to be able to actually scalarize that code, in which case it will work with the PTX backend. We also have not yet implemented atomics, and we're missing a large chunk of the built-in math functions for the libclc library. So now let's look at some of the issues that we've experienced as we've written this particular backend. So PTX itself is not actually machine code. It's not what's executed on NVIDIA devices. It's an intermediate representation, very much like LLVM itself. One point to make about this is that the register allocation we do in PTX is not final. For a given PTX code, the device code will have register allocation that could be done completely differently. And this PTX AS program itself is a black box for us. We don't have source code for it. We don't know how it actually works. So we basically have to guess in how best to generate PTX to generate the best possible physical device code. And the device code itself is not actually documented anywhere. So again, we have to sort of look at what's the output of PTX AS. We actually did disassemble the output to see what PTX AS is doing, to see what kind of device code we're actually getting out of it. We also have an issue in that we have an infinite register file. So like I mentioned before, PTX for registers has a declare before use semantic where we define what registers we want to use. So if we say we want 3 F32 registers, it'll define F0 through F2 for us, which we can then use. But there's nothing special about the name F. We can name it anything we want. We can create another F32 register and use it just like the F registers. So this creates a problem for us when we need to define the actual register file within the LLVM backend. So if we take in an example of PTX code here to show the effect that PTX AS has on register allocation, I can tell you that this PTX file uses about 118 registers. If we run the PTX assembler over it, it decides that it needs 23 physical registers to actually implement this. We can also artificially limit the number of registers that can actually be used. For those of you familiar with GPU code, we'll see the possible advantages of actually limiting this register file. So here we see we're limiting ourselves to 16 registers, and the assembler will actually generate the loads and stores from the stack spill space. So we've gone through a few iterations of trying to implement this virtual register file within LLVM. The first implementation just uses a very large register file. So we define on the order of 256 or 512 architectural registers for each type within LLVM. Of course, that's a very large number of registers, but we're relying on PTX AS to actually do final register allocation anyway. An advantage of this is it's very easy to implement. All we have to do is define the registers within the actual register table gen file. However, we also will need to handle spill slots here. If for some reason we actually generate more than, say, 512 registers of a certain type, we'll need to be able to handle the case where we need to spill one, in which case we'll actually generate additional registers in the PTX file that we artificially use as stack space. Our second implementation tried to be a little smarter. So here it will actually we'll use a very small register file and basically rely on stack spilling to implement the register file for us. So anytime LLVM determines that a spill needs to occur, it will need to know where to actually spill this and how to actually spill it. So what we do is for every spill slot, we will emit another register declaration in the actual PTX file and just emit copies to and from this particular register. Now, of course, this is much less trivial to implement than the first solution, and this gives us a lot of extraneous register copies. The hope here is that PTX AS will be able to see through this and optimize the code anyway. However, we found that that's not necessarily the case. So the third solution, and the solution we're actually using now, is to just not do register allocation at all. So we will physically disable register allocation within LLVM, and in the PTX file, we will emit the LLVM virtual registers. So, of course, at this point, the register file may very well still be in SSA form, in which case you'll have a very large register usage using virtual registers here. But we've noticed that PTX AS does a better job of doing final register allocation in this model. So even though the PTX file has 4 or 5 times the number of actual registers that are needed, it ultimately results in the best code. Another issue with PTX is when we do have to generate stack frames. So PTX itself does not have stack frames. So unlike other backends, we can't just create a stack pointer and add and subtract to it as we need more stack space. So we have a couple options. We can basically emulate a stack by declaring a array in the local address space, kind of faking a stack pointer and using that. We could also create a local variable for each stack slot and have the appropriate loads and stores from that. Or we could try to create a new reg variable for each stack slot. One nice feature about working with PTX is that since we have the infinite register file and we're actually emitting virtual registers, we don't need to worry about register spills. We're not doing register allocation, so we can't have a possibility of actually spilling registers. However, we still need to handle the case where the LLVM IR uses alloc that cannot be lowered down to simple register usage plus fees. So currently, we handle this by emitting a single local variable for each alloc, and then we will emit loads and stores to the local address space each time you load or store from the alloc in the LLVM IR. Okay, so that was meant to be an overview of the state of the backend, some examples of how we do things. Now, but by no means is this a complete look at the backend, but given the actual time constraints here, of course, we can only show a little bit. So now we're going to look at an example of actually using this. So we're going to look at a matrix multiplication kernel written in OpenCL. So when you look at a matrix multiplication example, of course, this is the most commonly used example whenever you take any kind of GPU course. And to make things simple, we're just going to say we have square matrices of size n by n, and we want to compute C as the product of A and B. We're again going to make it easy for ourselves and say we're going to use one GPU thread to compute each element of the output matrix. Further, we're going to use local memory as a way to cache data in our fast scratchpad memory, which will allow us to greatly improve the execution speed of this particular kernel. So if we look at what the kernel will actually do here, so assuming this is our output matrix C, and we have a thread that's going to compute this blue point here. What it's really going to do is compute a dot product of a row here and a column here. That's essentially what you do for a matrix multiplication here. And of course, since we're going to schedule a thread for each matrix element, we'll compute the entire output matrix C. To make this a little more efficient, we're going to use a tiled approach here. So assuming that each matrix is split into a 3x3 grid of actual thread blocks, we're going to compute this by computing the partial dot product across each tile. So we're going to start by computing the partial dot product of this partial row and this partial column. As we move across all of the actual tiles in the green area here, we will of course produce the entire result. What this gives us is the ability for a single tile to bring in the parts of the two matrices that it will actually need into shared memory or local, and be able to just load from shared memory whenever it actually needs data. So this basically decreases the amount of times we need to go to global memory, which is much slower than shared memory. So if we look at what Clang will actually do with this code, we see a few interesting things here. So first, Clang is going to generate our local memory buffers in address space 4, which is exactly as we had defined as the local address space. Second, we're using our PTX kernel calling convention here. And all of the built-in OpenCL functions, for instance, get local ID, get global ID, so on, those compile down into calls into these LLVM intrinsic functions to access the PTX special registers. We also notice that Clang itself will do some unrolling of the actual inner loop. So here, we're fixing our tile size at 16. So one thing we notice, if we look through the entire code, is Clang, instead of generating the actual loop for the inside, it'll just emit 16 copies of the inside. So we don't have to worry about this inner loop causing extra branching in our PTX kernel. And then, of course, Clang will go ahead and define the intrinsics that it actually needs. So if we look at the final PTX version of this, we see that here we're using a very large number of actual registers. However, we'll see in a minute that's not necessarily a problem for us. We also note that all the function calls to LLVM intrinsics here have now been compiled into reads of the PTX special registers. And all of our address computations will be factored out outside of our actual computation region here. So within our computation region, all we have are load, load, and then multiply, add. Load, load, multiply, add. We also see that the backend did fuse the multiply and add into a single PTX instruction. So if we look at what PTX AS will actually do, we see that it will need only 23 physical device registers to actually compile this code. However, like we saw before, we can also artificially limit ourselves. And if we define that we only want to use 16 registers for this particular kernel, for each thread, then PTX AS will go ahead and do that, but emit a 8-byte stack frame. Now, of course, no presentation would be complete without some actual numbers. So if we take this particular kernel and look at it on 3 different NVIDIA devices, and look at the performance of the OpenCL kernel over multiple iterations, and look at, for CUDA 4.0, the NVIDIA OpenCL compiler and the Clang OpenCL compiler using the PTX backend. The one thing we notice is for the 2 Fermi class cards, the performance is more or less equal. There's no real difference between the actual speed. For the older GTX 280 cards, Clang is actually doing a slightly better job. So here we actually have average execution time, so lower is actually better here. So the Clang times are actually now a little bit lower. So in the last couple minutes, just to conclude here, the PTX backend itself is being very actively developed. We only really have 3 main developers working on it, but we're still all very active in it. LLVM 3.0 marks the first good release of this backend. So if you download 3.0 or even trunk, you will have a very usable backend. It's already competitive with the NVIDIA OpenCL SDK, which isn't necessarily a surprise since you use LLVM too. However, this allows us to create a great platform for GPU research. So you can so instead of doing OpenCL source-to-source transformations, you can now do LLVM IR level transformations on your OpenCL code. You can go to this address to look at a collection of samples, of OpenCL samples that have build scripts to use Clang to do compile. And of course, since this is a part of LLVM, feel free to contribute bugs. Or I should say bug reports, not bugs. And special thanks to Shailing Chow, who was the original person that started this project, and then Dan Bailey, who's been a very big help in getting this working. So, any questions? Nope? Okay. Ah, yes.
Is it possible to add a JIT function into the like that?
JIT, not really, because there's not really a concept of JIT for this. I mean, you can't. I mean, you could at runtime use LLVM to actually generate PTX code and then load it using one of the NVIDIA SDKs, but it's not something you can really change while it's running or anything like that. Any place where you would get a benefit from doing JIT compilation. Yes.
What is the main reason of getting better runtime performance compared to NVIDIA?
That's a good question. I have yet to really determine why that is. It looks like for the GTX 280, it's a little more than just error, but I'm not. I mean, the performance isn't different enough that I really worry about it. I really don't know what the concrete reason for that particular example is yet. Yes.
With your register allocation, I work on the API backend at NVIDIA, and we actually did the exact opposite. We started out with virtual registers, and then we moved slowly using a subset of the infinite registers.
Mm-hmm.
Are you finding better or worse code generation? Or is that getting the machine level optimization?
So I really think the answer to that lies in the black box called PTX AS, where when we use virtual registers, it makes the job of that assembler easier to actually see through what dependencies actually exist. Where when we try to actually reuse registers, it's actually just confusing PTX AS and giving us worse code. Now, in terms of the number of registers that are ultimately used, the number of stack space that's ultimately used, it's pretty much universal that we're getting better results by using virtual registers. Now, if you also have control over final code generation, that might be a completely different story. The fact that we don't have control over that is a big issue for us. Yes?
Where are you planning to take this next? Do you have any plans for, you said it's a great platform for GPU compiler research?
So the short term is to finish it. Of course, we want to implement atomics and basically implement the entire PTX ISA. In terms of compiler research, a couple things we're looking at is doing some domain-specific language work to do automatic code generation for both CPU and GPU targets, so you don't have this issue where in order to write OpenCL code, you kind of need to know, you kind of have to be an expert in the actual hardware. So we want to try to create models that will allow you to more easier write applications like that. Yes?
You mentioned that PTX kernel functions could only be called by the host, and they cannot call their kernel functions.
Yes.
But OpenCL allows kernel functions to call their kernel functions. How is that implemented?
It's not.
So that model can be used with a compiler.
Well, I mean, so the restriction that kernel functions can't call device functions is a PTX restriction. So we need some way of figuring out how to do that. Now, I actually was not aware that OpenCL kernel functions can call other kernel functions. So that's news to me. I'll have to look into that a little more. Okay. Thank you.